We are Team 30, and this is our presentation for the 2026 Illinois Stats Datathon. I'm Noemia, and I'm here with Victoria and Anirudh. The objective. Synchrony Financial handles 4 million calls per month across 4 clients of customers. When workforce planning gets it wrong, the cost is not symmetric. Understaffing means broken service levels, abandoned calls, and SLA violations. Overstaffing means wasted payroll, but the damage is smaller. The scoring formula confirms it. The understaffing coefficient alpha is larger than the overstaffing coefficient beta. So we didn't just build a forecasting model, we built a model that knows which direction to be wrong. We were given 3 datasets. First, 2 full years of daily data, January 2024 through December 2025, covering call volume, handle time, and abandon rate across all 4 clients. Secondly, we were given 3 months of 30-minute interval data from April through June 2025, roughly 4,000 records per client at granular resolution. Third, a daily staffing schedule for all of 2025, the number of agents per day per client. August 25 is our prediction target. We held it out from training entirely. The data has gaps. We cleaned and addressed those before doing any modeling. 2 patterns drive everything in this problem. First, the intraday curve. Call volume is not distributed evenly across the day. There is a consistent shape, near zero overnight from 1 to 5 a.m., then a ramp up that peaks mid morning through early afternoon. This shape is remarkably stable across all 4 clients. The scale changes, but the curve does not. This is what makes interval level forecasting hard. You are not predicting one number per day, you are predicting a shape with 48 values. Second, the day of the week effect. Mondays are dramatically higher than Sundays across every client. The grouped bar chart makes this clear. Weekdays dominate. Any model that treats all days the same will misforecast both ends of the week.
We extracted 7 feature groups. Slot index and day of week captures the rhythms within a day and across the week. Weekend and holiday flags, which indicate a near holiday indicator for the days right around holidays, which get fed into the daily model as outside variables. Month picks up the broader seasonal trends, and rather than encoding client as a feature, we train completely separate models for each client, which comes out to 16 models in total. So every client's unique scale and behavior gets captured without any compromise. Our architecture has 2 stages, and each one does one thing really well. Stage 1 handles the daily scale. We fit a Serimax model with a weekly seasonal period of 7, trained on 2 years of daily data per client. Weekends, holidays, and near holiday flags serve as outside variables. This gives us a daily total forecast for call volumes, average handle times, and abandon rates for each of the 31 days in August. That works out to 12 SariMax models, which is 4 clients times 3 metrics. Stage 2 handles a shape within a day. A PyTorch feed forward network takes day of week as a 7-dimensional one-hot vector and outputs 48 interval weights through a soft max layer, which guarantees they always sum to 1. We train one network per client on 90 days of interval level data. For handle time and abandon rate at interval level, we use straightforward historical slot level averages pulled directly from the interval data. These metrics are more stable and actually benefit from that simplicity rather than needing a neural network prediction. So here's how the final call volume outputs come together. You take a SariMax daily total, multiply it by the neural network interval weights, and then apply a 7% upward bias adjustment. All values get clipped, so nothing goes negative, and abandon rate is capped between 0 and 1. We validate our approach by comparing it against a baseline using June's interval data. What the baseline does is compute the historical average for each combination of day of week and time slot. So it captures the typical weekly pattern in intraday shape, but it treats every Monday the same and every Friday the same. The chart here shows one representative week from June for client C, which was our highest volume client. The black line is actual call volume. The orange dashed line is the baseline, and the blue line is our model. You can see the baseline is flat across Monday because it averages through the peaks and dips. Our two-stage model adapts because Max picks up whether this particular day will be higher or lower than average. And then the neural network distributes that daily total across the 48 time slots. The key advantage here is structural. By separating how much today from when during the day, we let the stage specialize at what it does best. Here are our August 2025 forecasts across all three metrics and all four portfolios. The top chart shows daily call volume. You can clearly see weekly seasonality where Mondays spike and weekends drop, and the scale differences between clients are preserved. Client C forecasts the highest volume and client A the lowest, which exactly matches the historical pattern. Below that, handle times and abandon rates are stable day to day, but distinct per client, which shows that our model captures each client unique operating profile. The bottom panel zooms in a single Monday, which is August 4th, at a 30-minute level. This is the actual model output, meaning 48 interval prediction per client. The intraday shape matches what we saw in our EDA, which is a near zero overnight, a ramp through the morning, a peak in the afternoon, and a taper in the evening. That shapes exactly what the PyTorch network learned from the 90 days of interval data.
We optimize for the scoring formula, where the penalty workload component weighs understaffing more heavily than overstaffing. Since alpha is larger than beta, a forecast that is 10% too low costs more than a forecast that is 10% too high. Therefore, we decided to multiply all column predictions by 1.07, 7% upward bias, shifting our error distribution, where we accept slightly more overstaffing in exchange for slightly fewer understaffing events. This only applies to call volume because that is a metric that directly drives overstaffing and understaffing. The goal is to minimize the cost of error. Next slide. We compared our forecasted call volume against the August staffing schedule, using each client's average CCT and an 85% agent utilization rate. We computed how many calls each staffing level can handle per day. The four-panel chart shows each client's August forecast, where blue bars are forecasted daily call volume, and the red dashed line is the estimated staffing capacity. And when bars exceed that line, which we can see shaded in red, that's an understaffing risk day. Next slide. 4 directions for improvement with more time and data provided. First, given more interval history, a feed-forward network wouldn't really be used, but rather we would use an LSTM or temporal fusion transformer. 90 days isn't enough for a sequence model, which is why a more simpler architecture would have been preferred. Secondly, external signals with billing cycles data. Promotional campaigns and marketing events create predictable volume spikes, which aren't. Then cross-client learning. 4 clients share call center infrastructure, where one is busy, others tend to be busy too. A model learns these correlations and could improve predictions, especially for client A, the smallest and noisiest. Next slide. To summarize, we built a 2-stage hybrid model. Max for daily trends, which are 12 models covering 3 metrics across 4 clients trained on 2 years of history, and PyTorch for intraday distribution, with 4 feed-forward networks learning how call volume spreads across 48 half-hour slots trained on 90 days of interval data. The output is 1,488 rows of 30-minute forecasts for every day in August 2025 across all 4 clients. Call volume, customer care time, and abandon rate. The model is explainable in 2 stages, each with a clear purpose and goal, where separate models per client handle the 5 times difference in volume between portfolio A and C. Thank you.